So we are very pleased to have Kiumars Kaveh as our first speaker, who will talk about tropical vector bundles and matroids.
Thank you very much. Thank you very much to the organizers who gave me the chance to talk about this subject. It's great to see so many friends and familiar faces, and I'm relatively new to Matroids, and it's a little bit intimidated to talk in front of all the world experts on Matroids. But somehow I was dragged into Matroids through a study of vector bundles and toric varieties, and a study, of course, line bundles and toric varieties is a very classical subject and relates to piecewise linear functions and polytopes, etc. So it's I was interested and came into the study of vector bundles to see how much of convex geometry can be utilized in a study of vector bundles. It's not a very new subject, but has a lot of, I think, recent progress has been made in this area. This is a joint work with Chris Manon, my good friend and collaborator from Kentucky. As a tradition, I always draw pictures of my collaborators. Alternates between having beard or not having beard. It's a smile always there. So our preprints are these two, tropical vector bundles and matroids. This year posted on arXiv. The other one, toric vector bundles, valuations, and tropical geometry. And almost about the same time and exactly about the same time, Diane and Vivas Khan and Diane Maclagan came with the more or less exactly same definition of tropical vector bundle. It's more precise if I say tropical toric vector bundle, vector bundle on a toric variety, but from a different point of view. Of course, I have to put their paper, tropical vector bundles. It's also on arXiv. We coordinated to post it on arXiv at exactly the same day. And interestingly, both papers, if you abbreviate the name of authors, are KN. And the same year, same. And then I also have to mention Kalina Mincheva and all collaborators work on tropical vector bundle. They come from tropical scheme theory and propose a definition of the tropical vector bundle. I'm guilty of yet not completely studying their work, but looks like their definitions gives us a different class of objects. But I hope this week I can understand her work better, because she is here. Okay, so just a little bit of notation. Torus is capital T. I work over complex numbers, but the base field for the most part is not important for Klyachko classification of toric vector bundles. It works over any field, but just for simplicity, I take complex numbers. So T is n-dimensional algebraic torus. N is the co-character lattice, N is the dual character lattice. Later on, I tried to avoid using M and will use curly M for a matroid. I hope that will not be confusing, but M does not appear too much as characters. Okay, sigma is a fan, which gives a toric variety in the co-character lattice. X sigma is the toric variety of the fan. So as a basic example, which is one of the best examples to introduce toric varieties, toric variety of projective plane is this familiar fan with three maximal cones. And a toric vector bundle, the toric vector bundle is a vector bundle curly E or E over a toric variety X sigma together with the T linearization. So the linear action of T on E, the linear action on E, which extends or lifts action on the base toric variety. one can also define a toric principal bundle. More generally, that would be a principal bundle over a toric variety with an action of left action of T, which commutes with the action of G on the principal bundle, whatever the group is. And toric line bundles and toric varieties are well known, classified by piecewise linear maps. In integral piecewise linear maps, so send lattice points to integers and are linear on each cone on the fan. By the way, this vertical bars means support of the fan or union of cones in the fan. A lot of times, and many examples, the fan is complete, so this is just the whole vector space NR. And if A rho D rho is the Cartier divisors representing the line bundle L, then the piecewise linear map sends a primitive vector and a ray, so a ray generator to plus or minus depending on convention of coefficients of that prime divisor. So I'm assuming people are familiar with basics of toric geometry, but if there is any notation question, please stop me. And there is a little point, is that Cartier divisors actually corresponds by this correspondence to piecewise integral or integer piecewise linear functions. And then line bundles are Cartier divisors mod principal divisors. But that dividing by principal divisor or shifting the piecewise linear function by a global linear function is compensated by corresponds to picking the T linearization on L. So the line bundles do not correspond to piecewise linear function. Line bundles with the T linearization corresponds to piecewise linear. Okay. And in around 89, Klyachko class gave a very beautiful extension of classification of line bundles to toric, to vector bundles, toric vector bundles. Actually, Kaneyama gave a classification before him, but Klyachko's data of classification is much easier to work with and has been much more influential. This is a beautiful paper, and it contains so many material. In my opinion, it's like 5 papers condensed into one paper. And so, if this is a equivariant or toric vector bundle, the toric vector bundle, and if we can assign to it a fixed vector space, so we pick a point. We identify torus T with the open orbit in the toric variety, and then by fixing a point in the open orbit, which represents the identity in the torus. So, and then look at the fiber over that distinguished point or identity in the torus. This is a R-dimensional vector space. R is the rank of the vector bundle. So all the combinatorics happens in this vector space, and the data of the classifying data of the toric vector bundle will be a linear algebra data appearing in E plus some polyhedral or piecewise linear data. So it's a mix of linear algebra and polyhedral or polyhedral combinatorics. And kind of already having linear algebra suggests matroids may sneak in at some point into the story. Okay, so Klyachko to each ray, one-dimensional cone in the fan, assigns instead of a number as in a piecewise linear function, you assign a number to each ray in the fan. Here, instead, you assign a Z filtration by decreasing filtration by vector subspaces, something like that. And then filtration such that eventually it's 0 from one side and the other side is E, everything. So it's another way of thinking about this Z filtration is a flag of subspaces in E, but which are the jumps in the filtration. And then to each flag, which is a jump, you have to assign an integer which tells us at what index that jump is happening. So you can also think of a Z filtration as a flag labeled by integers, decreasing integers. Okay, so but and actually this is okay. I'll explain in the next slide how to construct this filtration. Is pretty easy. And then there is also an extension of piecewise linearity condition for piecewise linear functions to this situation. So if you have rays coming from the same cone, the corresponding filtrations should satisfy some compatibility condition or some linearity condition, meaning that they should come from a linear representation of torus. So T, and there is a representation of torus, a linear action of T on E, and then which means there is a basis of weight vectors and some weights for the action of torus. So some characters of how many characters and the basis of for E, such that these subspaces appearing in the filtration can be recovered in a natural way out of this linear data, weights and basis. The weights may not be obviously distinct, so this is how many characters maybe with repetition. Okay, so more precisely, each ith space in the row filtration is spanned by basis elements whose dot pairing or dot product with the primitive vector is bigger than the index. This looks little bit not straightforward for if you see it for the first time. I'll formulate it in a little bit later in a much more easier to state thing. Okay. Just to give you an idea, for the tangent bundle of Pn or P2, like whose fan is this and rays are this, you have 3 filtrations given by E from one side, 0 from the other side, and the one-dimensional subspaces spanned by first basis element, second basis element, and then minus V1, V2. Like corresponding vectors in the S vector space E. Okay, so it's not a difficult computation, but basically how one can arrive at this filtration data is looking at sections of or sheaf of sections of the vector bundle. Sheaf of sections of the vector bundle by denote by U sigma, the affine chart corresponding to a cone sigma, and then because you have an open cover, you have by looking at the restriction of the sheaf of sections to these open charts, you can determine the whole vector bundle or locally trivial sheaf of T modules. And then it turns out it's enough to look at the charts corresponding to rays. And then to know the T action, you need to know the weight spaces of this sheaf. And then a weight space, I forgot the U. A U weight space is determined. If you have a section, U weight section, it's determined by restriction to that distinguished fiber over identity. So by restricting the weights U weight section over the chart row, you get a subspace of your distinguished fiber, and this is the image in here I call E row U, and this subspaces as U changes become a filtration. Basically, they depend only on the dot product of U with the primitive vector, so you get a filtration, Z filtration, and conversely, out of these subspaces and filtrations, you can recover the space, the sheaf of sections, and one can show that this correspondence is a classification or equivalence of categories, blah blah. But actually, Klyachko's proof of this, his classification, is through transition functions. I saw some reason he doesn't use the sheaf theoretic approach. Anyhow, compatibility condition comes from the little lemma that your vector bundle restricted to each affine chart is not only is trivial, but it's equivariantly trivial. So it's isomorphic to trivial bundle, and then the T action comes from a linear action of torus on your vector space. So that is not difficult to prove because you have a T action. I think the more general without T linearization, it is also true. I think it's a result of Gubeladze, but it's more difficult. But because here we have a T action, it's not difficult. It's a little 2-3 lines through. Yes. So that's the story of the sheaf of sections, and then so the global sections are intersection of all these filtration subspaces for the correct index for all rays, and then there's U-weight sections, global U-weight sections, and global U-weight sections on an open chart are also intersection of this filtration space for rows coming from this your sigma, etc. So they contain all the information about the sheaf of sections and hence the whole vector bundle. And now the idea to graphicalize it is to replace the filtrations by the Z filtrations by flats in a matroid M. But I'll choose to say it from another perspective. For that, and making more connection with tropical geometry, I'll reformulate the Klyachko data a little bit. So each Z filtration can be thought of as a valuation on the vector space E. It's just R-dimensional vector space. It values in Z, or Z and infinity. I recall about vector space valuation, or what I mean by a vector space valuation is something that zero vector has value infinity, and only vector with value infinity. It extends the trivial valuation on base, the ground field. So for every vector, a non-zero constant valuation of vector and the multiple is the same. And it satisfies non-Archimedean inequality. These are in one-to-one correspondence with filtrations by defining all the vectors whose value is bigger than or equal to I to be the ith filtration space. And and then of course you can also talk about R-valued filtrations and then valuations, and then you have R filtration. So I define B tilde E as all R-valued filtrations on E. It's like a space of flags on E labeled by real numbers or integers, depending on what you want. Okay. So this, we actually realized that some years ago that this has to do with the Tits building of a general linear group in representation theory, which is a simplicial complex associated to the group, and the in simplices corresponds to parabolic subgroups, etc., etc. And this gave us a way to give a classification, extend Klyachko's classification to principal bundles. Anyhow, so this guy is a union of infinite union of vector spaces that also comes from building theory. So for each basis, to be more precise, basis up to a scaling. So for me, a basis and a scaling of a basis give the same thing. So you have a basis B1, BR for the vector space, and then you define the apartment corresponding to that basis. It's a subset of, it's a collection of valuations. I have defined it, valuations V on vector space or filtrations on the vector space, whose filtration spaces, all those EIs, are spanned by subsets of B. Are spanned by subsets of B. And one can see that this can be naturally identified with the R-dimensional vector space by sending a valuation which is in the apartment to its values on the basis element. So it's an R tuple of numbers. So basically, apartment of a B are valuations who are determined by the values on the basis elements. We also call them valuations adapted to the basis B. And because evaluation is insensitive to a scalar multiplication, this is the same for if you scale the basis element. And then these are linear algebra exercises to check that every valuation is adapted to a basis, because every filtration is spanned by a basis, and so on. And also it's an exercise that these apartments satisfy axioms of a building, but I skip that building theory perspective.
What is the extended part of this?
Ah, yes. Thank you for asking. The TITS building, the apartments are triangulations of a sphere. So we are basically considering cone over a sphere, which is a vector space. So we have some extra directions from the point of view of simplicial complex and building theory and combinatorics of a simplicial complex. Those are redundant. So in representation theory, building theory, they consider the simplicial complex as which is the building is a infinite union or union of apartments who are spheres, triangulations of spheres. For us, we have an infinite union of R to the R vector space. So that's what extended is.
It's the same as an affine building, right?
No, there are two versions of building, or at least two important versions of building. One is a spherical building, the other is affine building. A spherical building, this is a spherical building related to cone over the spherical building. Affine building would be for a group over a valued field. And actually that I will not talk about that story today, but if you repeat this story over for affine buildings, you will get classification of vector bundles over toric varieties or toric schemes over a DVR. Okay. That's another work with Chris and my former postdoc Boris. Okay. So Klyachko data can be, as usual, I'm slower than what I thought. So Klyachko data can be stated in a package in this shorter form. And actually this also has been in a different language, has been also observed by Sam Payne in an earlier paper, but we didn't know about his work at the time. We define a piecewise linear map, extending a piecewise linear function on the fan to something from the fan to this B tilde I, a space of valuations, or this building of GLE, such that for every sigma, that's the definition or the condition or in the definition of piecewise linear map. The restriction to each cone should send that cone to some apartment. That it could land in the intersection of apartments, we don't care. It should be at least land in one apartment. And because this guy has a structure of a vector space naturally, it makes sense to say that it's linear. So it should land in an apartment and this map should be a linear map. So if you can think of it a piecewise linear map, since you have an infinite union of vector spaces, which is that B tilde E, and you have a fan. So it folds it in a piecewise linear way inside this union of vector spaces. Sends it. That's what Klyachko data does, basically. And in that, and then you can also say that a piecewise linear map is integral, send integral point lattice points to lattice points, because this has a notion of lattice point, because which are the z-valued filtration, z-filtrations or z-valued valuations. Okay, so Klyachko, basically reformulation of Klyachko is that toric vector bundles or equivalence classes of vector bundles, isomorphism classes of vector bundles over X sigma are given by piecewise linear, integral piecewise linear maps to the building. And it's also easy to see or recover from this piecewise linear map the equivariant Chern classes and K-class of the vector bundle. This goes back to Sam again, Sam Payne, but with this, looking at this notion of piecewise linear function, we get some kind of little bit it's the same statement as Sam, but little bit said differently in our paper. So one can see that ith elementary symmetry in R elements defines naturally R elementary symmetric function or well-defined function on the space of filtrations or a space of valuations on E. By basically, if the valuation is adapted to a basis, by just looking at elementary symmetric functions of values of the valuation on the basis element. And it's the independent of evaluation or filtration can be adapted to different bases, but this definition is well defined. And same goes for exponential functions, sum of exponents of the values. So you have these two God-given functions on this building or extended building or a space of valuations. And then if you just compose them with your piecewise linear map, you get, in this case, you get a piecewise polynomial function. In this case, you get piecewise exponential function. And then these represents the equivariant Chern classes and K class of the toric vector bundle. It comes from localization in equivariant cohomology. And finally, tropical formulation of this data, which involves some choice. So now we have like, just to recap, we had a bunch for each ray in the fan. We had a Z filtration that was compatible in some sense, or they were piecewise linear in some sense. We formulated it as a piecewise linear map from the fan to a space of valuations or the building. And then we explained that Chern classes, K class can be read off from that picture. And by the way, this reformulation of Klyachko is basically saying that this space of valuations or building is in some sense classifying the space of the toric vector bundles. Maybe tropical classifying a space for toric vector bundles. I cannot make this because the maps to this guy correspond to toric vector bundle, but I cannot make it precise in a precise tropical language in what sense it is classifying the space. I think that would be a nice problem to think about. And as I mentioned, we extend this to classify, we define extended building for any algebraic group or reductive group. And then this classification extends to torus equivariant or toric principal bundles over a toric variant. And this, in a similar fashion, you can recover characteristic classes of principal bundle. Okay, so theoretical formulation, which then leads us to matroids immediately, is, so you pick a spanning set for E. I forgot to say a spanning set. And then take the linear ideal of relations among your vectors. And then you can define, you look at, we want to look at the Bergman or theoretical variety of this ideal or Bergman fan of the representable matroid. But first we notice that similar to the valuations and building, it is covered by some copies of linear space or R to the R, but in a piecewise linear fashion. So one look at take a basis in the matroid or in the spanning set and look at the maximal cone corresponding to this in the Grosvenor fan. GFL is the Grosvenor fan, and intersect it with theoretical variety of L. In fact, one can get this, and then we call it apartment associated to this basis. And we later realized Felipe has already studied this and has a different name for it and introduced this concept. I think, correct me if I'm right, Felipe is also here. Local tropical linear space. But because we were motivated by building theory, we still call it apartments with permission of Felipe. So if to each R tuple, this is similar to constructing a valuation. This is similar to this map, sending a valuation to its values on the basis elements. This is similar theoretical version of that, or matroid version of that. So to an R tuple of numbers, previously you could define a valuation for that adapted to the basis, but now you want to define a point on the Bergman fan. So for the indices which come from the basis, it's the same. It's the same number in this list, because this is actually it's better to say this R to the R is R to the E, the basis. If not, you take you add this you add your element in the matroid or vector to the basis, and then you have a circuit, a minimal circuit, minimal dependent set, and then you take the minimum of values of over the circuit, of course excluding your vector. Okay, so this produces a point on the Bergman fan, and then is a piecewise linear isomorphism between R to the R and some subset of Bergman fan. And one can check that if you have a piecewise, if L is large enough, or if the matroid or number vectors you pick, the spanning set is large enough. In fact, if it includes all the bases that appear in Klyachko data, or all the bases corresponding to each cone in the fan in Klyachko's classification, if it contains all of those, then you have this commuting diagram. So you have this piecewise linear map which goes to all the space of valuations, and then you can break it or as factors through a map to theoreticalization of L, or Bergman fan of L. So Bergman fan sits in the space of valuations. Okay, so yes.
What goes wrong if I choose a non-representable matroid?
So
I can take the tropical linear space instead of tropicalization of L.
yes, so that's the next slide.
Oh, okay.
But this part, there is no this part that it doesn't sit in the building.
Okay.
Yeah, it's just something, but it has it's a union of apartments in that sense, which are copies of R to the R. Everything works, but it just doesn't sit in the building. And then this is this can be seen as a can be encoded in a matrix, which we call a diagram of a piecewise linear map. So it's just a value of over each ray. Instead of a filtration, we think of it as a point on the Bergman fan. So it's an n tuple of numbers. Okay, so for each ray, we have a n tuple of numbers. So we can encode this into a matrix, which is diagram of the piecewise linear map, or diagram of the vector bundle, toric vector bundle, with the choice of the matroid we started with. So then, as you can see, it can be repeated for any matroid. So you have the Grosvenor fan, Bergman fan, and then you can define an apartment in Bergman fan as intersection of Bergman fan with the maximal cone in the Grosvenor fan. And the same, or another way, you can in the same exactly same way, word by word as before. Each apartment is a piecewise linear copy of R to the R, blah blah, all words. And then you can define a tropical toric vector bundle over a toric variety with matroid n, which may not be representable as such a piecewise linear map. So it just means that every cone lands in an apartment, and it's a linear map from the cone to the apartment. Okay. There is another, if you just switch the variables in the definition, you arrive at another definition, equivalent definition, which it's basically a vector bundle up to refining the fan. So you can up to pullback by toric morphisms. So there is no fan in this definition. So you can say that toric vector bundle, and then this is also works. It basically comes from another classification which appears in our paper, or reformulation of Klyachko as toric vector bundles at tropical points, but not tropical points over usual tropical semifield, but over the big semifield of piecewise linear functions. So if you consider semifield of piecewise linear functions on the 4-character lattice, and then you look at tropical points of your matroid, or points on the Bergman fan valued at this semifield, then this is same data as this. But there is no fan here, so it's basically this data up to refining the fan. And this is the tropical condition. But I'll be mostly concerned with this definition.
So can you say again what the input data is for this definition? So it's like a fan.
Second definition.
Maybe the first definition.
Definition. First is a fan and the matroid.
Okay.
So if I understand right, the classification of toric vector bundles now is a toric vector bundle is one of these piecewise linear things and a realization of the matroid.
So in the toric vector bundle, different matroids can give the same vector bundle.
Okay.
Yeah. The second definition in vector bundle case, toric vector bundle case, is valuation on the vector space E with values in the semifield of piecewise linear fund. These are in one-to-one correspondence with toric vector bundles up to pullback toric pullback. Or refining the fan.
I'm confused as to why the left-hand side doesn't seem to have a continuous part.
Sorry,
The left-hand side doesn't seem to have a continuous part. If I have two different realizations of the same matroid, there should be different vector bundles. Maybe I should ask you later.
yeah, so sorry, different realizations of the same vector bundle, same matroid give the same vector bundle. Is that your question?
As I understand it, and I should let you move on, if I have two different realizations of the same matroid, those should be non-isomorphic vector bundles. That's why I'm confused as to why the blue writing on this page doesn't seem to have some sort of continuous data on the left-hand side. Right, because if you go back to your commuting diagram, the map from trop L into B of E depends on the specific realization.
So there is no realization, of course, here. Yes.
So the vertical arrow,
So
the vertical upward arrow depends on the choice of realization.
sorry, this is the shorthand of writing of the Klyachko data.
Right.
Yeah, there is no matroid or realization here. But I was saying that if you pick a spanning set for E, you can factor it through this Bergman fan of the matrix. So, but in Klyachko, the way you can it is stated is a bunch of filtrations or a piecewise linear map to a space of valuations. There is no matroid. A priori, there is no choice of matroid.
I guess I don't want to tie up from.
Okay, maybe.
So they're making an additional choice. So they have a toric vector bundle, and then they choose a configuration of vectors.
Right.
So that every space that appears in the Klyachko filtration is spanned by a subset of those.
Right,
vectors.
that's where I understood. That's definitely what I understood, but then that's why I was confused as to why the blue line he had written there wrote classification of toric vector bundles, and on the other side didn't have the correspondence for choice of vectors.
I see.
And then this definition, this what I wrote in blue here.
But there's so that V is some sort of valuation, right? So that has some complicated filtrations built into it.
This curly V is a valuation, and there is again it's a valuation on a vector space, no matroid yet, but it's the data of it is some subspace.
It's not the ground set of the matroid.
No. I should have emphasized that. Sorry, my bad. I wanted to say this, but yes, so there's a confusion of the notation. E is the vector space, which is the distinguished fiber of the vector bundle. Yeah, sorry. Because we started with Klyachko paper and we kind of adopted his notation, we stick with his notation E for the vector space. It's not the ground set of it.
Okay.
My apologies for mix up with the confusion.
I
I forgot to emphasize that. Yeah, with abuse of notation, I use curly M as the ground set of the matrix. My apologies to the matroid crowd, which used to use E as the ground set. My apologies. So M is the ground set of the matroid. E is the vector space in the representable case the matroid or the ground set lives in. Okay, so that was the definition, and then first. Okay. First, I want to say that any matroid M comes with a natural toric tropical vector bundle, which we call it tropical toric vector bundle of the matroid. And because that's for the simple reason that there is a natural projection from the Grosvenor fan to Bergman fan. And it's similar to before, similar to definition of apartments. You basically pick a point, an m tuple of numbers, which I call W, and then you pick a basis in a maximal cone in the Grosvenor fan for a basis in the matroid, and then you keep the indices or coordinates. You keep the coordinates from the basis elements, but replace the other ones with this minimum formula to produce some point in the Bergman fan. Okay, so this is defined for each maximal cone for each basis, but it's independent of the choice of basis if a point is in the intersection of two maximal cones. So you get this natural projection, which should be familiar for people here, from Grosvenor fan to Bergman fan, which then naturally gives us a map from the permutahedral fan to Bergman fan. And by construction is piecewise linear in the sense which described before. So this gives us one of these toric tropical vector bundles. And then one of our results is we check that in the representable case it agrees with DEST tautological bundles on permutahedral toric variety Berget-Eur-Spink-Tseng.
But if you look in that paper, they're not toric vector bundles. They're equivariant with respect to a larger torus.
The torus is the torus of the permutahedral.
No, the torus is like it's like GM to the n and then GM to the n mod GM is the torus of the permutahedral, right?
So there is equivariant with respect to a larger torus, what we are saying.
Yes.
So but still it's equivariant with respect to the torus of the.
No, I don't think so. I mean, you can break the symmetry and then it will be, but like as defined in the paper, it's not.
Yeah, maybe we can talk about it afterwards. But there is little bit to say here. I said agrees. It's up to some dual and some things has to be matched here. Okay. But it's you take your linear space and then the orbit of this orbit closure of your linear space in Grassmannian, and then pull back the tautological bond sub bundle. That's okay. And then if you have a symmetric function, I'll finish soon in less than 10 minutes. So if you have it's a little lemma, not difficult. If you have a continuous symmetric function on R to the R, then it defines a map, a well-defined map by basically because of basis exchange on the Bergman fan. And composing, so in particular, sum of exponential functions or elementary symmetric functions give such maps, natural maps on a Bergman fan of a matroid, and composing them with the piecewise linear map defining the tropical vector bundle, we get definitions of equivariant K-class, equivariant Chern classes of your tropical vector bundle, which we think of as data of a piecewise linear map. Okay. And then we also verify that it agrees with again up to dual or some matching conventions, blah blah. It agrees with the Chern classes of tautological classes of BST. BST, which works for every vector, every matroid, and agrees with the tautological classes of in the representable case. So basically, one of our motivations was to give found combinatorial versions of bundles that have the tautological classes of BST. And then sheaf of sections also works in a similar way as in the toric vector bundle case. You have a rank of the matroid. You have I don't go too much into details. I'm running out of time, but you can for every affine chart and every character you can define this guy, basically repeating a story in the vector bundle case, in the toric vector bundle case, in the geometric case, would give you a flat in M, and then its rank would be the dimensional or rank of the space of weight sections, and global weight sections are intersection of this guy. So everything works basically same way, except that you do not, or at least I do not know how to make the check complex to define higher cohomologies because we don't have the boundary maps. But what we have, H0 we have, and H0 is good enough to, for every affine chart we have H0, and H0 is good enough to define Euler characteristics. So we have H0 and Euler characteristic, or for every character, so equivariant. H0 can be defined as alternating sum of, Euler characteristic for equivariant Euler characteristic for a weight, for a character or weight U can be defined as alternating sum of these ranks, as in the check cohomology. And then we say that higher cohomologies of E vanish if H0 is equal to Euler characteristic for every U. Okay. We do not have the higher cohomologies, but we can, if they vanish, the Euler characteristic should be equal to H0. I take this as definition of vanishing of higher cohomologies, or at least that's the term I'm using in this slide. And then we have, so far we have some vanishing of higher cohomology results, which is not that really that obvious. There is some tricks going to it to prove it, some non-trivial tricks. We can also easily define tensor product of one of these bundles, tropical bundles with line bundles. So if you have an ample toric line bundle for sufficiently large tensor power with an ample, higher cohomologies vanish. And then the question which I've asked my student to look at is if higher cohomologies of tautological bundle vanish. It's very related to BEST work. And this is an example I copied from our paper. So for the Fano plane, this is the diagram of a vector bundle with Matroid as Fano plane on the projective, the toric variety is projective plane. Okay, so we have 3 rays, and these are the corresponding points, tropical points, or points on the Bergman fan. And then, as in the toric vector bundle case, pretty much word by word, the space of sections, global sections, can be encoded in a collection of polytopes by polytopes called parliament of polytopes by Jabush, Diroko, and Smith. So that story also carries over to here. And then just find some final comments. So this definition of tropical toric vector bundle more or less immediately extends to toric schemes over a DVR, which are classified by simplicial complexes instead of fans, and evaluated matroids. Whose basically Bergman fan of evaluated matroid is a Bergman complex of evaluated matroid, and you can say a piecewise affine map between them. We have a notions of globally generated and ample imitating this. It is a tentative notions, at least the ample one, but basically repeating or imitating the toric vector bundle case. We have some partial results about the splitting into line bundles related to Klyachko's original results. And Herzebrück-Riemann-Roch, I was curious if there is a Herzebrück-Riemann-Roch, and actually there is. My student Suyan Chan. I'm happy to have a Korean student working on Matroids. So he basically verified that general Khovansky-Puplikov Herzebrück-Riemann-Roch for convex chains actually is this Herzebrück-Riemann-Roch for this tropical vector bundle fits into their general theory, and Erhard theory and all fits into the Khovansky-Puplikov general theory. This is it's in progress, it's still not out yet. And then it's also in progress working out Khovansky-Tessier inequalities or log concavity for intersection number of Chern classes. This should come out out of tropical Hodge theory of June and collaborators. This is also one of the projects. Again, a vanishing of higher cohomologies for tautological bundles. And then an interesting question, which I'm sure Diane is also interested in, is extension to other tropical varieties or base weighted fans, or connections to F1 geometry. Does this definition fit into general framework of Matt and Oliver and others? And I think I can stop here. And also this definition should go through to define tropical principal bundles for Coxeter matrix. Okay, thank you very much.
For Kiumars?
Yes.
You said this in the beginning, but you didn't repeat it. So is your definition exactly the same or exactly equivalent to Diane's?
They have a valuated Matroid in definition, I think. Yes. Up to that, if you have a usual Matroid, yes, it's exactly the same.
Any other questions?
Could you say a bit more about this Erhard theory, asterisks, and the Hertzberg-Riemann-Roch? What are their last points in all folks?
So basically, if Erhard theory is about Euler characteristic or H0 for as number of lattice points, and Khovansky-Puplikov extended to convex chains. That theory, convex chain, is a linear combination of indicator function or characteristic functions of polytope, or an element of polytope algebra. Okay. And it turns out that over last summer with Khovansky, we realized that actually it's immediate. One can assign to each toric vector bundle one of these convex chains. It's kind of immediate from Klyachko's data, and then so their theory applied to that convex chains. You have volume, you have number of lattice points for every convex chain, and this gives exactly Euler characteristic and everything.
Okay.
It's also related to branch cover of fans in Sam's earlier work.
Can you comment a little bit more about H0 in case maybe of a tautological bundle of Matroid? Like, what is that number?
Yes, I don't know what's the combinatorial interpretation of that number. I like to understand better.
Is it the number of lattice points of something?
Yes, it is. By definition, it is.
What is that something?
It's it is to each element of the matroid ground set, to each element in the ground set, you can assign a polytope given by some inequalities. And H0 would be sum over all lattice points. H0 in general is sum over all lattice of polytopes that contain, you can look at polytopes that contain that character. Sorry, this is U weight. Sorry.
Model relation.
So the U weight rank of the U weight sections is a rank of the subset of the matroid which the corresponding polytopes contain U. Does it make sense? So in that example, yeah, like you have each polytope, each one is labeled by each polytope is labeled by an element of the matroid, and then you take a character and then you look at which polytopes contain it. Each polytope has a matroid, it gives us a subset of the ground set, and rank of that subset is the rank of H0U.
And is the theory set up in such a way so that that subset is actually a flat?
Yes.
And we are expecting that this number is equal to the Euler characteristic of the topological vector bundle, which can be computed in some completely different way.
Yes, I think so.
We have some non-empty subset of the authors of the PET. Do you know?
Yeah, in the realizable case, one of actually H0 is known to be something like number of codes. Something derived from just number of codes. So a lot of times it'll just be zero.
Other questions? Yeah, okay, then we'll have a big break at Rubenstein or outside or the IS4S, and then we're going to resume for Lucas talk.